Now we are going to start with the P block elements. As you know that in periodic table the elements are actually grouped according to their nature. That means we have different blocks, and in different blocks different elements are present, right. As we know that in a periodic table we have 4 blocks, that is S block, P block, D block and F block. For the systematic study, the periodic table has been classified into 4 blocks, as this group 1 and group 2 comes under the S block, right. This is the P block, this is the D block and this is the F block. This you have already done in the chapter periodic properties that we did early in the early chapters. So you are familiar that how the different scientists made an attempt in order to classify the elements, and finally what kind of atomic table is acceptable, and you know that this is the atomic table which is worldwide acceptable, and so we know that it is being divided into 4 blocks for the systematic study. So now we are going to start with the study of P block. So we are going to study about the P block. So the first thing is that which elements come under, or you can say fall under the P block, or you can say what is the condition necessary to be a member of the P block. So those element is said to be a member of P block in which the last electron enters any one of the 3 p orbitals of outermost shell. See, I am going to explain you now how. Suppose if I am talking about neon, right, we know that atomic number for neon is 10, right. If I am going to write its electronic configuration, it is going to be 1s2, 2s2, 2p6. So here the valence shell is this second shell, and in this you can see that valence electron, the last electron enters the p orbital. The last electron enters the p shell, that is the orbital of the p shell. So that means it is a member of P block. It means it is a member of P block. So all these groups which fall under P block is from 13 to 18. So if we talk about all of them, right, so their last electron enters the p orbital. That means their last electron enters one of the 3 orbitals of the outermost shell. And one more thing, that p orbital should be the valence shell. For example, if I write an electronic configuration of sodium whose atomic number is 11, so it is going to be 1s2, 2s2, 2p6 and 3s1. Though it has the 2p orbital, 2p shell, but it is not the last shell. Here the valence shell is S, right. So it is not a P block element, it is a S block element. So that means don't get confused that it has 2p, so it is also having 2p, so it is going to be the member of the P block. No, it should be the last shell. It should be the last shell. So that means this is a member of P block and this is not a member of P block, but because here the last electron does not enter into the any of the orbital or any of the p orbital of the p subshell, because here the last valence shell is in S, right. So that means first thing is clear that how to determine that which element belongs to P block or which element do not belong to P block. So the element will belong to P block only if its last electron enters any one of the 3 p orbitals of outermost shell. That means that the p has to be an outermost shell. So as we know that if we talk about p subshell, it has 3 orbitals which are designated as px, py and pz. Right, and we are already familiar with the rules of filling these orbitals. We know that each orbital can accommodate maximum of 2 electrons and that must be of opposite spin. You know that. So that means this p subshell, which is having 3 orbitals, can accommodate maximum of 6 electrons. It can accommodate maximum of 6 electrons. So that is the reason that we have 6 groups which fall under the P block. As you can see, there are 6 groups in P block: 13, 14, 15, 16, 17 and 18. 1, 2, 3, 4, 5 and 6. Because there it can accommodate only 6 electrons. So therefore we can have the 6 groups which fall under the P block. So that means the group which is coming or falling under the P block ranges from 13 to 18 group. It ranges from 13 to 18 group, right? So this is our 13 to 18 group, and in this probably the filling of 2p, 3p, 4p, 5p, 6p orbitals are taking place. With their last electrons, like in this the last electron enters the 2p, then that means it goes on increasing. So in one group the last shell is 2p, in the other the last shell is 3p, in other it is 4p. So like this the filling of electrons is being done here. So this is the 13 to 18 group, got it? Now if we talk about the total number of electrons that come under the p block is, then the total number of electron is the 30 elements. 30 elements are there in total in the p block, right? So I think you know now that which element is called as a member of p block, what is the condition which has to be fulfilled, and why there are 6 groups that fall under p block. You know the reason, that because it can accommodate maximum of 6 electrons, that is why it is having a 6 groups, and these are the groups as you can see. And if we talk about total number of elements, then it is 30 elements, and in this progressively the filling of 2p, 3p, 4p, 5p and 6p is taking place, right? Now if we talk about the general electronic configuration, now we are going to talk about its general electronic configuration. So general electronic configuration of this p block element is ns2 np, which can actually vary from 1 to 6, right? Because we know that when the S subshell will be filled, then only we are going to fill the p shell, right? So it has to be fully filled, then only the p is going to be filled. And how many electrons p can accommodate? According to group, the electrons which can be accommodated in p it ranges from 1 to 6. So in this we see that in some it is 1 electron, in some it is 2 electrons, like ns2np1, it can be ns2np2, it can be ns2np3, we will see that, right? So this is the general electronic configuration of p block elements. So what we will see that the general electronic configuration is going to be same as ns2np 1 to 6, but somehow the inner core is going to differ. Obviously the inner core is going to differ because the element which is having an atomic number 31, it is going to have different kind of the subshell, right? And if we are talking about the one which has a 6 atomic number, then obviously it is going to be different. Like if I take an example of carbon and silicon, so atomic number for carbon is 6. So the electronic configuration is 1s2, 2s2, 2p2, right? So n is 2. NP can be 1 to 6, so it is 2. If I talk about the second member of 14 group, that is silicon, the atomic number is 14. So it is going to be 1s2, 2s2, 2p6, it becomes 10, then 3s2, 3p2. So in this you can see that in the first member, the last shell is the second one, because 2s and 2p is being filled, and here though the electronic configuration is same, it is ns2 np2 only because it is same for the same group, but still the number of shell is different. Here the filling of 3s and 3p is taking place. And if I will write the configuration for the next member germanium, it is going to be 4s2, 4p2, and if I am going to take another example of 10, so it is going to be 5s2, 5p2, and for lead it is going to be 6s2, 6p2. So like this the filling of this thing will occur, right? I think you got it, that how the shells are progressively filled. So this is what is the electronic configuration. So what we are seeing that in each group the valence you can say general electronic configuration is same, but the inner core configuration is somehow different. The inner core configuration is different, due to which the physical properties, right, like melting point, boiling point, right, density and all, as well as the chemical nature, or you can say the chemical property, is going to show a certain kind of difference. So due to, you can say that like though they belong to a same group, but still you can show a gradation in properties, or you can see actually the difference in the properties. The reason is that though they are having the same electronic configuration, but still the inner core configuration is somehow different, and that is the reason that they possess, or you can say they show different physical and chemical properties, or we get to show gradation in physical or chemical properties. So this is the reason behind, right? So now if we talk about the oxidation state, let us talk about the oxidation state. So if we talk about the oxidation state, each group is going to have a group oxidation state. Each group is going to have a group oxidation state. That means this oxidation state will be shown by all the elements of the same group. Though they can show a variable oxidation state also, but the group oxidation state is going to be same for all the elements. So now how to find that group oxidation state? Suppose if I am talking about the 13 group, right? So its group oxidation state is probably equal to either the number of like if I will write its electronic configuration, I know boron is 5, right. So if I will write its electronic configuration, it is going to be 1s2, 2s2, 2p1. So that means for this, the general electronic configuration is ns2, np1. So either the group oxidation state is equal to the number of s and p electrons, that is 2 plus 1. So either the group oxidation state is equal to the number of s and p electrons, or how you can find the another way is that you can actually minus 10 from, you can actually minus the group number from the 10. So if you will minus the group number from the 10, then also you are going to get plus 3. So by either way you can actually find that the group oxidation state is either equal to number of s and p electrons, or you can actually minus the group number from the 10, and after that you will get the group oxidation state. Like if you will see the group oxidation state for this, so its general electronic configuration is going to be ns2 np2. So either you can say that it is directly equal to 4 plus 4, or what you can do is you can minus the group number from 10, then also it comes out to be plus 4. So likewise for this it is going to be the electronic general electronic configuration is going to be ns2 np3. So it obviously it can be plus 5, and you can get this 5 by minus by subtracting the 15 from the 10 also, and like for this it is going to be plus 6 and it is going to be plus 7. So likewise you can actually find the group oxidation state. So group oxidation state is actually you can say oxidation state which will be shown by all the elements of the same group. But what we have observed actually, that in group 13 and group 14 and in group 15, right, the group oxidation state is you can say that group oxidation state is more stable for the lighter elements. Like in 13, 14, 15, the lighter elements like is boron, this is a boron family obviously. So these are the lighter one, this is the lighter one, this is the lighter one. So the one which are lighter in mass, so they will be present above, because as we move down mass is increasing. So for the lighter elements we see that group oxidation state is more stable. But as we move down, then what happened, like if I talk of group 13, I will write boron, aluminium, it is gallium, indium and thallium, right. So for this, the plus 3 oxidation state is mainly shown by the lighter elements. But as we move down, then which oxidation state become more stable? That oxidation state which is 2 unit less than the group oxidation state, that is the 2 unit less means plus 1. So that means for the heavier elements, it is the state which is stable is 2 unit less than the group oxidation state. So that means if the group oxidation state here is plus 3, so on moving down plus 1 is more stable. Same is applicable for the 14 group also, like the group oxidation state is stable plus 4 for the lighter one. As we move down, plus 2 becomes more stable, because it is always going to be 2 unit less. Similarly here, if plus 5 is going to be the group oxidation state which is stable, then on moving down 2 unit less, it is going to be plus 3 which will be stable. And the reason for this is the inert pair effect. It is the inert pair effect we will discuss when we will start with the chemical properties. It is actually like, just for a hint, I just want to explain you that inert pair effect is actually the reluctance of the s electrons in the participation in the bond formation. That means the s electrons, as they are not shielded properly by due to filling of D and F, so the nuclear charge actually increase on them, and as a result the s electrons are tightly pulled by the electrons and they do not participate in the bond formation. And when they do not participate in the bond formation, only the p electrons are going to participate. That is why as we go down this thing, we need to subtract the s electrons from the oxidation state, that is it becomes 2 unit less than the group oxidation number, right? But if suppose you are not getting it now, so no need to worry, because when we will be starting with chemical properties, we will be discussing the inert pair effect in detail, right? So here what you can do is that you can actually remember this, that in 13, 14, 15 group, the group oxidation state is given, but as we move down for the heavier elements, then the oxidation state which is stable is 2 unit less, and the reason is the inert pair effect. Just make yourself familiar with the word inert pair effect. We will be discussing when we will start with the chemical properties, right? So this is what is the oxidation state. Apart from the group oxidation state and apart from the 2 unit less oxidation state, there are certain kind of variable oxidation state also which is shown by the elements, right? So this is what about the oxidation state. Now if we talk about the general chemical behavior, we will see that in a periodic table we have S, P, D and F block, right, in which we have typical metals. In P we have another group, in D we have metalloids, and in F we have rare earth metals. But out of it, the P block is a kind of block which contain metals also, non-metals also, and it contains metalloids also. It has 3 of it in it. It has metals also, it has non-metals also, and it has metalloids also. So like if we will see the P block, we will see that out of these elements which are the metalloids, the typical metalloid is the silicon, germanium, and then it is arsenic, antimony, tellurium. These are the typical metalloids. And the elements which are present above like boron, carbon, nitrogen, phosphorus, oxygen, sulfur, these are typical non-metals. That means the elements which are present above, they are non-metals, in mid they are metalloids, and the one which are present below, the one which are present at the bottom, you can say that they are typical metals. I am not talking about the 18 group, right? I am talking about these, actinium, polonium, bismuth and all, they are typical metals. So you can say that in a this is a group for the like if you say that this is a P block. So here we are going to get non-metal in this region, right here. In this region we are going to get non-metals. In mid we will have metalloids, and at bottom we are going to have metals. So that means this group has 3 of it. It has the elements which are lighter, they are non-metals. In mid it is metalloids, and as we move down we come across the typical metals also in this block, right? So this is the P block. And moreover, you are familiar that what is the difference between metals and non-metals. You know that metals have low ionization energy, and in comparison the non-metal has high ionization energy. And you also know that when metals and non-metals combine, they combine by an ionic bond, because there is a large electronegativity difference, right? But when the 2 non-metals combine, because due to less electronegativity difference between them, the bond is typical covalent in nature, right? And moreover, you know about the oxide nature also, that if we talk about the nature of metal oxide, then metal oxides are basic in nature, and if we talk about the non-metal oxide, it is acidic in nature. And the one, if we talk about the oxides of metalloids, we know that it is amphoteric, that means having an acidic as well as basic character. So as we have three kind of elements in this block, so like as I told you, in the upper case we have non-metals, so that obviously the non-metal oxides are going to be acidic. So in the above portion we have acidic character. In the middle we have the amphoteric character because we come across metalloids, and at the base what we get is we come across the typical metals. So we know that metal oxide are basic in nature. So we can say the above like on the top we have acidic character, then moving on to an amphoteric, and from amphoteric we move on to a basic character because we come across the metals. So this is a general you can say general chemical behavior of the elements which are included